So I think we're going to get started now-ish or maybe in a minute. I have one very short talk that I was planning to give just to kind of, if people didn't know anything about dark matter with LSST, kind of cover that. But I'm planning to have most of the session kind of be discussion and small group discussion. So if you guys want to participate and you're in the back, it might make more sense to sort of move forward, but you're also allowed to stay there. Cool. But I think we can get started. Oops, with one of the computers. Okay, I just want to give a reminder that there's a code of conduct we should follow, and I mean, we've seen these this week. Be nice to each other. And for this session, I think we will plan to be having some virtual participation. So I have Yao here is going to be monitoring the chat, and and if people raise hands, we'll let them talk. So yeah, so I think for this session, I'm going to kind of give a quick intro into what we're thinking about with some of the dark matter constraints with LSST. And then I was planning to kind of just have us go around both online and in the room and talk about what we're excited that either is related to dark matter, or maybe whatever probe you're excited about if you don't study dark matter at all, maybe something dark matter adjacent. And then I wanted to spend some time kind of talking about with the early data, if there were things we should start planning for to really be able to kind of hit the ground running as we get started with LSST. Cool. And I wanted to start by giving a little intro. The hat that I am currently wearing is that I'm one of the co-conveners with Nora Shipp of the Dark Matter Working Group in the Dark Energy Science Collaboration. Nora is joining us online. And the goal of our working group is to sort of use LSST data to really use a variety of astrophysical probes to understand dark matter and sort of the microphysics that govern it. And so what, yeah, as I explained, there's a lot of different ways that we're planning to do this. And so this working group really touches a lot of different science collaborations within LSST and a lot of different areas within the DESC. And so kind of one of the overriding messages that I want to give out today is that if you are interested in dark matter and would like to get involved, even if you're not part of DESC currently, new members are very welcome, and we'd love to have you. Cool. So I just want to spend a little while, for those that maybe don't know, talking about how we're kind of thinking about constraining dark matter with LSST. And the sort of the ideas we've been thinking about are kind of summarized on this slide here. And in the top left, well, maybe I'll jump ahead a bit. So we generally think of things as being cold dark matter, but then there are other models that we can imagine or changes cold dark matter. And here's an example that's warm dark matter. And what hopefully you can see is that a lot of the small details here, so on the left, it's showing a simulation with cold dark matter, and on the right is warm dark matter. In the warm dark matter simulation, the substructure is a lot smoother. And so that there's kind of less small details there. And so a number of the probes that we've been working on so far are really looking to kind of see if we're sensitive towards how much substructure we see at different times, and whether we can start to differentiate some of those models we have. And so that can include probes such as strong lensing, where you're looking for small scale fluctuations. That's kind of shown in the top left there. We're also looking at structure density variations in stellar, or hoping to look at density variations in stellar streams, as well as doing careful accounting of the galaxy halo connection for ultra-faint dwarfs around the Milky Way and other galaxies in the local volume. We also think that we'll be using LSST will be sensitive towards doing weak lensing constraints with some nearby dwarf galaxies acting as the lenses, and that and additionally, like the micro lensing surveys from Rubin will be sensitive to if there's a population of primordial black holes, we'll be able to put further constraints on that. As part of the DESC, we're planning some projects that use the 3x2 constraints, so the main cosmology analyses that are being done in the DESC, that those are also sensitive to, for example, like axion behavior, if that has effects kind of farther in the past. And then we've also identified a number of kind of local probes with anomalous stellar energy loss, so like the white dwarf luminosity function, and we can see effects in maybe like core collapse supernovae and stuff, so the behavior of stars. So there's I guess the point here is that there's a wide range of probes that we expect to be available with LSST, and we would love to really kind of gather a lot of people that are interested in those analyses and make progress there. And yeah, so sort of here's an incomplete list that I sort of talked through a little bit just now, and yeah, I just kind of wanted to leave it up there, and so I thought that it might be good to sort of initially go around the room with anyone who wants to share, and just to get a sense of who's in the room, and maybe also who's online. We can raise hands and do that, and just sort of start a discussion just to see what people are interested in around the room. And then using that, we can kind of organize into groups and think about what analyses we want to do with kind of early data. So I think my plan was to, at this point, to start kind of going around the room and talking about what people are interested in. I can go first. So I'm Peter Ferguson, as I said, and a lot of what I've been thinking about recently has been whether we can use stellar streams and nearby galaxies, sort of near field cosmology, and put constraints on dark matter that way. You want to go next?
I've worked on minimum halo mass, especially through Milky Way dwarfs and strong lenses, but starting to think about stellar streams. I've worked on large scale structure, and I'm working on halo profiles for dwarf galaxies, and definitely very interested about how far we can push that with LSST.
Hi, I'm Gautam Narayan. I'm the analysis coordinator in DESC, and my primary interest here is to make sure that we have a pipeline that gets us end-to-end for this analysis, and what do we need to put into simulations and other sorts of data to test those pipelines.
I'm Brian Miller from Gemini and NORLab. I'm working on DE-CAM surveys right now of nearby groups, looking for dwarf galaxies and star clusters, and eventually getting kinematics of those to look at the matter distributions.
I'm Shimmy from postdoc at NORLab. One thing I'm working on is survey for low redshift gas clusters to measure their mass distribution and galaxy population. So one useful thing is to look at the substructure distribution in those mass maps, because their distribution can tell us the self-interaction dark matter. Things like that.
So I'm Jan de Antonio at Brown. I'm also interested in nearby galaxy clusters. I'm also working on this similar survey. What I'm interested in doing with LSST is trying to match, use the galaxy clusters, in particular the relationship between the ICL and the dark matter mapped by the gravitational lensing, to try to look for signatures and check for consistency with the dwarf galaxies, because there are things in terms of constraints that require a cross match over multiple length scales.
My name is Christopher Stubbs. I failed to find WIMPs. I failed to find machos. I'm really interested to know what the dark matter actually is. And what I'd love to talk to people about at this meeting, in the top right-hand corner, is the energy balance in stars and actually how that impacts the absolute flux calibration of LSST. Because if Gaia tells us distances, we haven't really focused much on absolute flux calibration, and it's central to that issue. And I think I know a clever way to do it, and it's more of a non-project afterburner endeavor, and I'd like to know whether we should go do that or not.
Hi, I'm a graduate student from University of Delaware. I have not worked on dark matters. I think that it will be very interesting to study dark matter in LSST.
Hey everyone, Tansu Dailan. I'm a recent assistant professor at Washington University. I guess on this slide, I do focus on two things. One is strong lensing, and especially what's known as gravitational imaging of small subhalos in strong lenses and their perturbations. And the other is a more recent project I'm working on for searching for compact objects using microlensing, primarily based on test data right now, but I do want to work on that using LSST as well.
Hi, my name is Nima Sedagat. I do deep learning for transient detection with LSST. I kind of accidentally sat around this table, but so I am, from this slide, I'm interested in large scale structure analysis using unsupervised learning from big data, which I think should be possible with LSST, but I'm also interested in digging for fainter transients, which I believe is going to be useful for finding some signs of dark matter. Thank you.
I'm Keith Bechtel from University of Wisconsin-Madison. I've historically worked mostly on the minimum halo mass, but I'm interested in learning more about probes of dark matter with large-scale structure.
I'm Yao Yuan Mao, University of Utah. I usually go by Yao, Leahy pronouns. I work on nearby dwarf galaxies from both fully resolved dwarf galaxy to like fully unresolved dwarf galaxy. I'm interested also in weak lensing of dwarf galaxies. I'm also very interested in the organizational aspect of this work. Like I was advocating, the funding for dark matter science with Rubin, and also because, as you can see, this work spread across a wide range of science collaborations, like thinking about how do we collaborate and communicate across that range. Do you want me to run through?
I'm Duncan Wood from UC Santa Cruz and Skip. I've worked on large scale structure before, but more recently thinking about microlensing, discriminating between free floating planets and PBHs, both smaller and slightly larger than solar mass.
Hi, I'm Renee Nichols. I'm also from UC Santa Cruz, and I'm interested in weak lensing shear.
Hi, I'm Adrian Shestakov, also from UC Santa Cruz, and really just here to listen in, to be honest.
And I'm Steve Ritz from UC Santa Cruz, and there is a correlation. And I have also, I guess you could say failed, but I would say we put some great limits on WIMPs. And it's amazing to me with the data we're going to have with Rubin that we can't do something really great. I'm interested in obviously the halo types of things, but I'm also working with these guys on some novel ideas for lensing.
Okay, I'm Zhao Yu. I actually not working on the science part. I'm working on the more technical part on the, for the workflow processing with Panda. But I'm interested in the dark matter topics. I used to work in gamma ray energy range for dark matter, but not continued then. So I'm interested to know how Rubin can do these things.
I'm William Lindstrom. I am a software developer at Las Cumbres Observatory, and I work on Tom Toolkit. And so I'm basically here making sure I understand the use cases that might come out of DESC, and so we can support that as you guys developing your Toms.
Hi, Riley Clark, graduate student at the University of Delaware. I'm just here to listen and learn about dark matter.
Okay, this is CK Chang. I'm local in Stewart. I'm actually part of the AGN science collaboration, but we don't have too many AGN people, so I come here. But anyway, so I'm also interested in black hole and compact objects, so I want to learn from you guys.
I'm Ilana Urbach. I'm a postdoc working with Chris Stubbs at Harvard, and I'm here to listen and learn.
Hi, my name is Harshit. I am a grad student from the University of Washington. I work with the Rubin data management team, and I'm here to learn and listen.
I'm James Buchanan. I'm a postdoc at Lawrence Livermore, and in a past life, I was a particle physicist who also failed to find WIMPs. Now I focus on probabilistic modeling of faint galaxies, which might put me on the top middle there. And I also co-lead the blending working group in DESC.
Hi, I'm Hajan from Yonsei, Korea, and I'm a research professor at Yonsei University, but I'm interested in really the dark matter distribution in especially the emerging galaxy clusters. And I'm really wanting to be that your working group, a member of your working group. But currently I use the super hyper Kim data to measure their mass and also reconstruct their mass distribution. And also I combine all other the multi-wavelength data like XMM Newton, Chandra, and LOFAR, the radio data, to construct their merging scenarios. So good to see you.
Hi, I'm Atharva. I'm a PhD candidate from Taiwan. I'm working on calibrating the U-band in the galactic plane, and I'm interested in the stellar overdensity monosaur streams.
Hey, I'm Kai, data management Square intern. I'm just here to learn a little bit about dark matter.
Hello, I'm Tim Eifler. I work at the University of Arizona. I'm interested in some dark matter models like self-interacting dark matter, dark energy interactions, and how they might impact the density field that we can model and observe.
Hello, I'm Anthony. I'm a PhD student at Brown. I'm working with Jan right now. My main interest is studying the distribution of dark matter in galaxy clusters using weak lensing.
Hi, I'm Tris. I work on data management in Princeton, and I'm just here to learn.
Hi, my name is Rob. I work on the Telescope and Sight software team, and I'm here to learn a little bit more about dark matter.
So I'm going to tell you an inspirational story as I hand this back to Peter. 25 years ago, when I was the project scientist for what we then called LSST, and I would give these sales pitch talks, I would say my favorite time domain LSST project was microlensing of a strongly lensed type 1a supernova detected in LSST. And I said that tongue in cheek, but now like for real, that's a really cool thing to do.
Great. And I guess if anyone online wants to kind of introduce themselves and say what they're into, maybe raise your hand and yeah, we can call out your name.
Nora.
Hi, I'm Nora Shipp. I'm co-convener of the DESC Dark Matter Working Group along with Peter. I'm interested in stellar streams, both in using streams in LSST to look for evidence of subhalo interactions and constrain the minimum halo mass, and also extending studies of populations of satellite galaxies across the spectrum of tidal disruption.
Simon.
Hi, my name is Simon Bierer at Stony Brook. I'm working in DESC and strong lensing science collaboration. I do mostly strong gravitational lensing, but I'm interested in combining different probes of small scale structure to learn about below the galaxy formation threshold structure.
Martin.
Hello, I'm Martin Mackler from the National University of San Martin in Argentina. I'm mostly interested in microlensing, so having a census of maybe primordial black holes with microlensing. And I'm also joining the strong lensing science collaboration. So I'm also interested in dark matter in that context.
Here.
Hi, everyone. I'm Keir Rogers. I'm postdoc at Toronto, and I'm interested in large-scale structure constraints on dark matter models, in particular thinking about how to theoretically model non-cold dark matter models in structure formation. And I've also been working on stellar streams as well, and thinking about how they would look in simulations in non-cold dark matter scenarios.
That's all.
Hi, I'm Tessa Geltema. I'm at UC Santa Cruz, and I hear there's a contingent in the room. In this context, I'm interested primarily in like halo profiles, particularly on like galaxy cluster scales. I do various things with clusters, and also strong lensing. So strong lensing for the halo profiles, but also micro lensing types of constraints.
Thanks everyone. So now that we sort of have a general idea, I guess if anyone else wants to raise your hand, now's the time. We good? Okay. Now that we kind of have a general idea of what people are interested in, I thought it could be interesting to sort of think about what early data is going to look like from LSST, and imagine that many of you have sort of seen this before, but in other sessions here. But we are going to have this early science program with the public alert stream and the 2 data previews, and that's going to be happening in the next year and a half or so. And what I kind of wanted to maybe focus on, I think that at least I'm more familiar with kind of the static science, so that's what I put up here, but we can also talk about the alert stream that we're planning to have kind of 100 square degrees that are to 10-year depths in UGRIZY, and overlap that with the deep drilling field. And then we're also planning on, with commissioning data, having sort of 1,000 square degrees in GRIZ down to year 1 depths, or about 26 magnitude. And so I thought it could be kind of a fun exercise to sort of get into small groups with people that said something that sparked interest with you. And so this presentation, which is linked in the Slack channel or in the agenda, there's a link to it here. We sort of have template slides. And so I was thinking that we could maybe get into small groups or group up online and spend about 20 minutes kind of filling out a slide where you just talk about what you would imagine doing with some of the early data, and kind of what needs to happen to get there, sort of start thinking about that. And so I think that, this is data we could use to sort of test algorithms and really understand a lot of the infrastructure that is going to need to happen. Yeah, yeah. So yes, it's linked off the PDF. If you can get to this slide of the PDF. It's not a bookmark in this. Oh, yes, I probably should have posted it as a message. It's bookmarked in the Slack channel, and then it's linked on this slide of the PDF. So yeah, so I think that there's a lot of really awesome science that we can do with early data, and I just wanted to sort of break up into small groups and think about it for a little while, and then we'll come back and kind of talk about that with a larger group. Any questions? Cool. Well, you can do nearest neighbor if you want, or you can scream your favorite probe very loudly and hope that like-minded people can find you. I don't know, there's not that many of us. But yeah, feel free to just like group up with the people around you if you want, or if you know other people that are working on similar things. Let's reassemble and talk a little bit about what different small groups we're talking about. Unless anyone has objections, I think I'm just going to go kind of in order through the slides that ended up there. And if someone can talk about them.
Duncan to talk about the thing we did decide. So we talked about a couple of things. One was this issue of whether we can use the distribution of baryons and dark matter in clusters. And we decided that the SV and early science data is probably not a large enough area to guarantee that we will have enough clusters in the deeper areas. And we weren't sure how well the sky subtraction will work in the wide once we have with only a few samples. And so that's unlikely to be a first 6 months paper, right? It might if the sky subtraction works better than we think it might. But we did come up with something that might work.
Yeah, so the deep drilling fields, if we're gonna try and integrate to 10 or 20 year depth during science validation, we're gonna have a very high cadence of images on the order of hours, maybe less in some cases. Hopefully in multiple filters, although we weren't quite sure about that. But yeah, you can use that high cadence to look for relatively low mass, maybe Jupiter or less mass lenses as either PBHs or free-floating planets, and then hopefully use the timing distribution you find there. If you find something basically bimodal, then you could, hypothesize some different population of planets versus PBHs. So yeah, it would be a nice way to potentially find both. That's a real simulation from Roman data, I think. Colleague of mine at UC Santa Cruz.
I guess, do you have a sense for like, do we expect multiple or microlensing events to show up in commissioning data?
If we can find them. If we have, it partially depends on the pointing. Yeah, the DDF would be hard because it'll be extragalactic, probably, almost certainly. If there's something more toward the disk, then it's possible. Yeah.
Tesla has a comment. Tesla.
Oh yeah, I just wanted to say I had just talked to Nolan and Will about the free floating planets thing a couple days ago. So on that in particular, I mean, that's different than PBH, of course, like, non-galactic fields are fine, but yeah, you'd need a galactic field. But also from that conversation, it sounded like we'd need observations with much higher cadence than what we'll get in the nominal surveys. So you need them spaced, the observation spaced much closer together. But it is,
continue. Sorry.
They were talking about like minutes.
Yeah. I mean, a few minutes. I mean, so the DDFs, if we're trying to get to 20 depth, it could go down to something like 15 minutes. So it could be very rapid in certain fields. But yeah, you're right. Roman's more optimized for these small masses, but you could look for, somewhat larger masses.
Yeah. No, I'm not, I think it's good to keep in mind. I actually, I think Nolan's actively working on making some predictions. So yeah.
I think they're meeting right now.
Jan, did you want to say anything? Or?
No, I think Duncan made the point that I was going to make, which is that the general survey's cadence isn't particularly good, but the particulars of trying to get to high depths on the deep drilling field actually makes this a better first year case than it is a multiple year case. in some case, in some sense.
So just a quick comment on that. I think the primary limitation on pushing down in mass for primordial black hole microlensing is the finite source of the star that is being lensed. And the optimal strategy for that is high cadence imaging of the Large Magellanic Cloud, focusing on white dwarfs that are there as the source stars. And actually HST has shown that you can pick out the population of white dwarfs and make an estimate from surface brightness of how many are there. So if this group thinks that's a highly meritorious experiment that requires video mode imaging on fields in the LMC, that's something that should be expressly requested.
This is a good idea. Considered that, but haven't simulated that yet.
Great. Okay, first catalog of gravitational lenses.
Well, I made that slide. I wasn't really in a discussion, so I could focus on the slide. So what I basically want to mention here is, at first we need to find a sample of strong gravitational lenses, and we can then stare at them and see whether they flicker. And we expect about maybe one supernova going off in the 1,000 square degree, and in this time during science verification, maybe we're lucky. But certainly during year one, we expect about a dozen lens supernova, and we can study magnification biases, microlensing that comes into a place. And the same we can do with multiple lensed quasars. Those we already know a lot, and we're gonna have light curves already in year one, and maybe find anomalous caustic crossing events or and things like that. And generally making a large sample that we can focus on follow-up of a known characterized selection function understood sample. Yeah, that's points that I made here. I'm sure there's some, Tanzu is in person, there may be some other people doing strong lensing as well.
Hey, Simon, this is Gautam. So this is, I think, very tractable both with the SV surveys and with year one data. And it would be really helpful to start getting a catalog of potential lens sources, even so clusters, whatever else, where you expect to find some of these sources that we can put into the alert brokers as a watch list. So when we start getting alerts, we can trigger, and there will be alerts with high latency, even in science, even in the SV surveys. So in principle, we should be able to test this, especially if there's another telescope, like say PanSTARRS, that has a known active lens system at the time with some kind of supernova.
Yeah, people working on it, hope also for Euclid, and I also see Martin Marco's hand, who probably just says that, yes.
Yes, indeed. So yes, just to mention that from Gautam's comment, we are doing this with the Think broker. So we are providing Think with a large number of lens candidates to build this lookup table.
Martin, can we have that catalog just desk-wide? I suspect that we'll want to have multiple brokers active, and I don't want a single point of failure during SV, especially. I'd rather have all of the brokers be watching this.
Yeah, sure. This is the work of a student who has put together this large catalog of candidates. And one thing we want to do is to make a visual vetting of those candidates, since not all are good strong lens candidates. So as soon as we have this vetted list, yeah, we can provide it. I mean, if you want the non-vetted one, we are fine sharing it too. But I think it would be more useful to have this more final catalog.
Okay.
So we can reach out, yeah.
I will follow up with you.
Yeah, and this is also then Plessio Bohm may also be in the loop as the
right. Yes.
In
yes.
in kind in DESC. Yeah.
Great. Let's go to the next one. This is Yao.
Right. So the idea is pretty simple. Once we have the data preview out, we will be finding the smallest galaxy that we have be able to see in those catalog. The idea is that should be able to find, I don't know how many, but X ultra faint dwarf galaxies. Most of this will probably be in the Milky Way, but also like maybe slightly outside of Milky Way. You know, they will be ranging from 100 to maybe 10,000 stars. You know, supposedly we will have the photometry good enough for controlling the red-giant branch of this group of galaxies. And then, you know, we can say a little bit about how that might already be constrained on warm dark matter, fuzzy dark matter based on, you know, the assumed galaxy halo mass relation.
Do you like will this be successful if we just use the current star galaxy separation we have?
I don't think so. I don't know. I don't know. The abstract has a sentence saying that we might need to refine the star galaxy separation. That's my gut feeling, but you know, the magnitude is so low that I don't think we have a lot of experience.
Yeah, I can just comment briefly. I mean, so already Hypersuprime Cam detects dwarf galaxies that, you know, in the DES footprint, for example, that are not detectable in DES. So, you know, I think there's definitely discovery potential here. Even I guess what I'm saying is that even a baseline star galaxy separation should, you know, should have significant discovery potential in the southern hemisphere in general. 100 square degrees is not a large amount of area, so for these rare objects, there's a chance, right? That's Poisson probabilities.
Keith says it's worth doing.
Before we move on, I just want to say that if you can add your names to the slide, if you create a slide, that would be very helpful.
This
So I guess a bunch of people with poor judgment took the bait of talking about whether there's any merit at all and thinking about looking for anomalous energy transport. I think we concluded it's potentially interesting. I think there were well-founded reservations based on modeling uncertainties, observational uncertainties, and whether this would actually provide interesting constraints. I don't think, I for one don't know the answer to those questions. And whether or not to take the additional steps to actually arrive at answers, I think is a question that's unresolved and on the table.
Could you give like maybe like a sentence or two on what like anomalous energy transport is in this context?
Yeah, so basically imagine just hypothetically that the people who do modeling of stellar atmospheres could do a really good job, which in white dwarfs, actually, arguably they can. And if there's some energy transport mechanism other than just the typical photon diffusion outside of stars, then we'd see that energy leakage as being a mismatch between observations and models. But to do that, we have to measure the absolute 4 pi integrated flux coming out of some known star, right? So that requires two things. One is knowing its distance, and the other is knowing the flux in absolute watts per square centimeter per whatever kind of units, right? So for bright stars, Gaia tells us distances with sufficient fractional uncertainty that millimagnitude absolute calibration becomes important. So if Gaia gives us parallaxes to an appropriate subset of stars, to what extent are those appropriate targets? And what would we have to do? What's the right way to say it is, what's the intellectual marginal gain as we improve the absolute calibration of LSST for photometry? I think these stars would be so bright that they'd be in the twilight survey that we would do to extend the magnitude range to brighter stars. But this requires a lot more homework to determine whether it's even worth pursuing. Any, I don't know, other friends who were in the discussion, if there's anything to add or correct.
Right, it all makes sense. It's not obvious what kind of transport mechanism, because we talked about the neutrino, which I don't still understand. Like, how do you distinguish between the neutrino flux, which is also okay. Yeah. Anyone else?
Great. I think that's the last slide I had here. Does anyone else want to speak up and say anything, even if you didn't make a slide, or anyone online? Cool. In that case, I think if that's, yeah, I think that that's kind of all I had planned. If you want, we can hang out and discuss a little bit, like kind of infrastructure wise, what we need to make. If there, I think that we brought up, for example, that it would be good to maybe improve stellar selection. Yeah.
I have some suggestion for discussion topics. So I mean, this is more like, again, on the organizational side. So one question is about, like, how do we advertise to the public in terms of how Rubin can help with dark matter science, what are the tech line? Because as we can see, like, a lot of the dark matter constraint coming from a convolved set of, like, from the observation to the constraint is a pretty complicated path. And so how do we, as we are talking to both the public and funding agency, how do we make that easier and just more accessible in a way, so that we can kind of, be more clear than what we're actually doing as a group.
It might make sense to rank order some of the proposed ideas in what this group thinks is most feasible and focus on the first few that really are the things that you could get done in 1.5 years. There are things that we might just need too many resources for, even if they're potentially possible with early LSST data, but others are much more tractable.
Gotham, what do you mean by resources? You mean in terms of external data or in simulations or?
External data simulations, more than just that, just personnel even. If there's nobody actually willing to commit to leading a project, you don't get a paper out.
One other point I did want to make is that a lot of the projects that aren't in this list will need work in the first 1.5 years, because even though, for example, for galaxy clusters, there won't be enough clusters to make an interesting dark matter paper, we'll still need to test it on this data to see, so that in year 3, we'll have enough objects to do a test. So there's work that's not captured by this that we'll have to do.
Yeah, I mean, I think that's a really important point here. I mean, I think while there's definitely some discovery potential in the early data, like in the early science program, I think that there's really enormous opportunities in terms of demonstrating methodology, characterizing systematic uncertainties, basically piloting a lot of these studies. And I think those could still be like extremely interesting papers, right? Because what they could basically be, being able to make, much more sensitive forecasts, or, much more robust forecasts. And, I think in some ways it's actually like very exciting from the standpoint of like, it brings in all this sort of like creativity of the analysis, and the sort of like the stage of figuring out how to do these studies, right? So I mean, I think it should be emphasized that even if the constraints are not necessarily groundbreaking, that these could be exceptionally like interesting and impactful papers. The topic that I have not heard people bring up yet is simulations. And that can start now. Or already has been in progress, right? But you know, that's something that impacts almost all of these probes in some respect.
So I want to comment on the simulation comment because I think one difficulty there is like the if we're going like if we're actually like trying to constrain specific property of dark matter, then the needed simulation actually can be very different for different probes because they probe like different properties. And so there's no easy way to run like, you know, a few simulation that can be shared with all the different probes. Maybe we need to think about this like in some different ways, like maybe come up with like effective, you know, kind of effective modification to the simulations so that we don't need to, you know, just come up with new simulation for every single observable. But it's definitely an area that I think is a little bit on the development at this moment.
So on the simulation front, there I think we are, meaning the cluster thing is in a slightly better sense in that part of what Argonne is already doing fits this this test. And it's mostly just coordinating with the simulators to get out of their simulations the things we need, as opposed to getting them to run the simulations, which is I don't want to say it's an easier problem. It's a different sort of problem.
I was just wondering what you see the difference between what you get out of simulations that you might not get out of similar precursor data from DCAM or something.
Oh, sorry. When I was referring to simulations in this case, I was not referring to pixel level or catalog level simulations. You know, I'm not referring to representations of LSST data, but rather referring to simulations that capture the imprint of dark matter microphysics on structure formation. And body simulations and hydrodynamical simulations. Potentially, you know, with cold dark matter as well as alternative dark matter models.
I think Tesla raised her hand.
I just wanted to second Keith's call for simulations or discussion of simulations because, you know, for sure, you know, a lot of the probes that we want to look at, you know, can also be mimicked by baryonic effects, you know, within the constraints we currently have. So, you know, you can't run every simulation ever, but there's only, you know, a small number of simulations that have alternative dark matter models in them, and even fewer that have that and baryons. And then, you know, forget about different versions of feedback and stuff. So I think that's a very good point in terms of distinguishing signatures of baryonic effects and dark matter ultimately. Nora has a hand up now.
Yeah, I just wanted to advertise, Peter, I don't think you mentioned this yet, but within the DESC Dark Matter Working Group, we're actually planning on organizing a discussion specifically on simulation needs coming up soon, I think at the end of September. So specifically what simulations we need to think about gathering and running to prepare for dark matter constraints with a lot of different probes with early LSST data. So if anyone's interested in talking about this more, I think that's going to be our telecon the last week of September, but we'll definitely send out more information about that.
Nora, if I can quickly add, there's also the sprint week at CMU in October, and it might be a good outcome to actually have some small sprints defined that folks can start working on at the September meeting.
Yeah, that's a great idea.
Great. Well, I think that is enough for now, unless anyone has anything they want to say. Thank you guys so much for coming to this, and like Nora just said, if you want to get involved with any of the dark matter work that we're doing in DESC, or even just want to give a talk on what you're thinking about, we're very open for that in the dark matter working group, and feel free to contact us. And we're planning to sort of over the next couple months have some dedicated telecons to some of these different probes. So looking at simulations as well as strong lensing, and yeah, but we'll be communicating about that. And yeah, I think that's all I got. Thanks so much, guys.